Hi everyone, I'm Mahta Masumi and welcome back to my channel where we dive into everything geodesy. In today's video, we'll be exploring a key aspect of our field, which is the Earth and its gravity field. Understanding this relationship is crucial to many geodetic applications, and I'm excited to break it down for you. As I've mentioned in previous videos, geodesy is a science that focuses on measuring and understanding Earth's geometric shape, how it's oriented in space, and its gravity field. Basically, it's all about mapping out the Earth as accurately as possible. But just to refresh your memory, I'm bringing this up again today because understanding Earth's gravity field is a huge part of geodesy, and it's something we can't ignore when we want to talk about measuring the planet accurately. Now you might be thinking, why is gravity so important in geodesy? What does it have to do with accuracy? Well, gravity is actually one of the key factors that affect how we measure the Earth. It's not just about how heavy things are. Gravity impacts everything, from the shape of the planet to the orbits of satellites. And when we are talking about precision, even tiny variations in Earth's gravity field can affect measurements we take on the surface or from space. So, the more we understand gravity, the more accurate our measurements of distances, height, and even time become. Isaac Newton, in his famous Law of Universal Gravitation, explained how every object in this universe attracts every other object with a force that depends on their masses and the distance between them. This law is represented by this formula. But actually, this formula calculates the magnitude of the gravitational force between two bodies. However, to fully describe the gravitational interaction, we need to specify not only the magnitude, but also the direction of the force by using the vector form of this formula. Now I'm going to explain the vector form of Newton's law of universal gravitation. We'll start with the general formula and then modify it to determine the gravitational force of the Earth on objects whose dimensions are negligible compared to the Earth. Like when we want to calculate the gravitational force on a satellite orbiting the Earth or determine the weight of an object on the Earth's surface. So, in this slide, we see the basic formulation of the gravitational force between two bodies when their dimensions are considered negligible compared to the distance between them. I mean, this distance is much larger than the dimensions of these two bodies involved. So, in order to convert the previous formula to one that deals with direction and magnitude, we should multiply it by a unit vector. A unit vector provides direction without altering the magnitude, and it just defines the orientation of the force. As we know, the unit vector is obtained by dividing the vector by its magnitude, which essentially normalizes the vector to have a magnitude of 1. This makes the vector neutral in terms of magnitude, allowing it to represent only the direction. So the final equation would be this one, where we have magnitude and direction. In this slide, we consider the case where one body, such as the Earth, is significantly larger than the other body, such as a satellite or an object orbiting around the Earth or on Earth's surface. To calculate the gravitational force between the Earth and the small body, we treat the Earth as being composed of many infinitesimally small mass elements. So, we consider this body as being made up of many small elements like dB. As we know, mass is a product of density and volume. So for small element, we have dm equals sigma times dB, where sigma is the density and the distance r, and dB is the differential volume of the element. Now we can rewrite the basic formula for gravitational force by substituting the differential mass dm into the original formula, and this gives us this formula. Now, in order to find the total gravitational force exerted by this body on a point, we sum all these differential forces. Since the body is continuous, this summation is done through integration. Since g and m are constants with respect to the integration over the volume, they can be taken outside the integral. Also, in three-dimensional space, the volume element dv is given by dx, dy, dz. So, because of this reason, we use a triple integral to sum up contributions over the entire volume. Thus, the total gravitational force is the integral of the differential forces over the entire volume of the body. This equation helps us study the gravitational force exerted by the Earth on objects whose dimensions are negligible compared to the Earth's size, like small objects or satellites. However, to precisely analyze Earth's gravitational effects, we need to know how mass is distributed within the planet, because the gravitational force depends on the density of the Earth at different points. Unfortunately, Earth's internal density distribution is only known approximately. This figure shows one such model proposed by Bullen in 1963 based on seismic data. All seismic models assume that the Earth is perfectly spherical, meaning the density varies only with distance from the Earth's center or depth, like you can see in this image. So, in a symmetrical Earth model, density is uniform at any given depth but varies with depth. It means the Earth looks the same in every direction from the center. Because of this symmetry, the gravitational force at any point on or above the Earth's surface always points directly toward the center of mass. Also, in such a model, the strength of the gravitational force you experience only depends on how far you are from the center of the Earth, not on the direction you are facing. As a result, outside or on the surface of a spherical object like the Earth, the gravitational pull felt at a point can be calculated as if all the mass of the Earth were concentrated at a single point at the center, and this point mass at the center would have the same total mass as the actual Earth. But it is already known that the gravitation of such a particle is given by this equation. So if the needed parameters are approximately these, then the mean value of the gravitational attraction on the surface of the Earth is actually this one, where m is the mass of the attracted particle. As the gravitational force field is not perfectly radial, this value is only a mean global value. While we have discussed how the Earth's mass and density distribution affect the gravitational force, Earth's rotation introduces another important factor, which is centrifugal force. As the Earth rotates, objects on its surface experience an outward force called centrifugal force, which acts away from the axis of rotation, and its direction is always perpendicular to the instantaneous spin axis. The nature of this force is apparent because it vanishes as soon as the object stops rotating with the Earth, showing that it depends entirely on the Earth's rotation. The formula for centrifugal force acting on an object due to the Earth's rotation equals the mass of the object multiplied by the square of the Earth's angular velocity multiplied by the object's perpendicular distance from the axis of rotation. The centrifugal force is greater at the equator than at the poles because of the Earth's rotation and how this force depends on the distance from the axis of rotation. At the equator, the large distance from the Earth's axis makes the centrifugal force stronger, At the poles, the small distance results in a much weaker or nearly zero centrifugal force. Gravity is a net force we experience on Earth's surface, resulting from the sum of the gravitational force and the centrifugal force. Net force is the total force acting on an object when all individual forces are combined. At the equator, centrifugal force is stronger, so gravity is weaker. At the poles, centrifugal force is nearly zero, so gravity is stronger. It is usual to work with accelerations rather than forces. When we write the vector equation for the gravity force, it can be seen that the gravity force is expressed as a product of the term in braces, which is g, and the mass m of the particle a. From Newton's second law, it is known that force is the product of acceleration and mass. As a result, this vector is denoted by g and is called the gravity acceleration vector. A gravity anomaly refers to the difference between the expected gravitational force, which based on an ideal symmetrical Earth, and the actual measured gravity at a specific location. Now, about causes of gravity anomalies. As you know, there are some variations in Earth's density. Denser or less dense materials beneath the surface can cause gravity to deviate. Besides, geological features can cause gravity variations. Large features like mountain ranges, ocean trenches, or mineral deposits can influence local gravity. Moreover, Earth's shape and orientation are effective too. Earth's equatorial bulge and centrifugal force also affect local gravity measurements. We have two types of gravity anomaly. Positive anomaly happens when measured gravity is greater than expected, and negative anomaly happens when measured gravity is less than expected. About its importance, we can say that gravity anomalies help scientists understand Earth's subsurface structure and geological activity. They are useful in areas like mineral exploration, oil discovery, and studying tectonic activity. The gravity field is a vector field, meaning at every point in a space there is a vector. However, working with a scalar field is often simpler because only a single number is assigned to each point in order to represent how much potential energy an object has at that location due to gravity. Because the Earth's gravity is irrational, it can be expressed as the gradient of a scalar potential. In other words, there exists scalar fields like VR that can be written in this form. This V, which is a scalar field called the gravity potential. We know that F equals mg and both F and g are vector fields, so both F and g can be written in terms of these potential fields. So this W, which is a scalar field, is known as the gravity potential. Since the gradient is a linear operator, we can use it as a sum and have this formula. Now, the question is, how can this potential be used to show the irregularities seen in the gravity field caused by mass distribution? The answer is the potential can be used to depict the irregularities in the gravity field by analyzing its equipotential surfaces and lines of force. The gravity equipotential surface is defined as a surface where the gravity potential is constant, meaning that the gravity force is always perpendicular to this surface at any point. Due to mass distribution irregularities within the Earth, the equipotential surfaces are irregular. Where the gravitational field is stronger, the equipotential surfaces are closer together. Where it's weaker, they are further apart. So they can show where and how gravity changes due to irregularities in mass distribution. This is the end of this chapter. Thank you all for your attention and stay tuned for what's coming next.